Hello everyone. In this video we're going to learn how to use Excel to perform two-way ANOVA analysis. Let's first have a look at the bulk experiment. The objective of this experiment is to test if there is any difference between two test media, bulk, manual, and among three plating methods, CNW, HT, PNO. The response Y is the top of the knock-nut. So here we have one factor. This is plating methods. There are three levels of this factor: CNW, HT, PNO. And this is the other factor, test media. And we have two levels, bulk and manual. Within each cell, we have 10 replicates. So in total, is 2 by 3 by 10 is 60 observations, 60 data points. Now in the Excel spreadsheet, this is the data we have. This is CNW, HT, PNO, and this is the bulk, this is manual. And obviously here we could not put all 10 replicates in one cell, otherwise we will not be able to perform the analysis. So that's why we separate all the replicates into different rows. Now let's click data. We have data analysis tab, and we're going to use this tool to perform the two-factor ANOVA. So here we have two options: two-factor with replication and two-factor without replication. In this case, we have two-factor with replication because each combination, CNW and bulk, we have 10 replicates. HT and bulk, we have 10 replicates. So this is a tool we're going to use, two-factor ANOVA with replications. Now the input range. So this is our input range, and we include labels too. Now, rows per sample. How many replicates? We have 10 and 10. So the significant level 0.05. Output range. Let's put the output range here. Let's click OK. So this is the results we got for the two-way ANOVA. So let's interpret these results. So this is the summary statistics. Over here we have CNW and B. So this summary statistics is for example, for CNW and B. Here we have 10 data points, and the sum is 174, average because 174 divided by 10 is 17.4, and then we can calculate the variance for this cell. And the same thing for PNO, and we have 10, 305 is summation, and 30.5 is the average, and 131 is the variance. And the total here, this is the total for this row. We have 30 observations, and the sum, this sum is 826, and the average is 826 divided by 30 is 27.5, and the variance over here is 113.36.09. And we do the same thing for CNW and M, and so we got this column. And then the total. This total is for CNW total. So we have total for B and total for M, and then this column CNW total, this is the total for CNW. So we have 20 observations. The sum of this column is 343. The average is using 343 divided by 20. So it's 17.15, and the variance of this column is 12.76579. And same thing for the column of H and T. We got this column, and the column of this, we got P and O, the total. Now let's have a look at the ANOVA table. So this is the ANOVA table. Before we integrate the ANOVA table, let's go back to the lecture notes. In the lecture notes we have, so this is a model. We decompose So each observation, this is else replicate for the i's level of factor A and j's level of factor B. So that's why we have IJL. So I denotes the factor level, factor A level. J denotes the factor B level. L is the replicate. Alpha I, this is a global average. Alpha I is the main effect for A. So the main effect for A. And the beta J is the J's main effect for B. Omega Ij is the interaction effect between A and B, and this is random error. So if we use this model to do the estimation, this will be what we are going to do. And here we have I dot dot. What does this I dot dot mean? So I dot dot means if it is Y1 dot dot. If it's I1 dot dot, it will be this row, the average of this everything over here. Why? Because I dot dot means we're averaging over J and over L. So we're averaging over all factor B and over all replicates. We only consider I, the factor A level I. Same thing, if it's dot J and dot, it means we are going to do the average for J and average over So in the ANOVA table, we are decomposing the total variation into 4 components. The first one is the test media, the variation from the test media. And then we have the variation from the plating method and the interaction effects between test media and the plating method. Then we have the random variations. So if we add all these sum of squares together, it should equals to the total variation. So here, this is the samples. So in all the rows, we have testing media. And columns we have plating methods. So this is sum of squares from the testing media. This is the sum of squares from the plating method. And this is interaction effects, and this is within each group, each cell, this is random variation. If we look at the analysis of body experiment table over here, we have the same number over here. And then we have degree of freedoms. So the degree of freedoms, actually, we have 2 test media, and 2 minus 1 is 1. And plating methods, and we have 3 plating methods. 3 minus 1 is 2. Interaction effects is 2 minus 1, 3 minus 1, so it's 1 by 2, so it's 2. And this one is 2 by 3 by 9. So this is 2. 2 by 3 by 9, 6 by 9 is 54. And how many data points we have? Oh, in total, IJN. I is number of testing media. We have 2. And 2 test media. And we have 3 plating methods. 2 by 3, 6 by 10 replicates each. So that's 60. 60 data points. 60 minus 1, 59. So if we add all the degree of freedom, it should equals to 59. And if we add all the sum of squares together, it should equals to the total sum of squares. So the mean sum of square equals to the sum of squares divided by degree of freedom. So this column is actually this column divided by the degree of freedom, this column. So the F statistic, this F is actually this 821 divided by 36. And this is 1145 divided by 36. 9 is 332 divided by 36. And this is a p-value for each f-test. So the f-test is trying to compare whether the variation from the testing, let me change this one. This is the testing media, and this is the plating method. This is interaction, and this is a random variation. So the f-test, this f-test statistic is trying to compare the variation from testing media and from random, whether they are in the same level. So the higher the value is, you see the p-value is smaller, that means testing media has higher variation than the random variation. And this one, plating method, is also very significant. They are significant than the random variation. And the interaction also significant. So over here, the conclusion from the ANOVA table is, so the conclusion, both factors and their interactions are significant. So multiple comparisons of CNW, HNT, and PO can be performed by using two-key method with k equals to 3 and 54 error degree of freedoms. So they are all significant based on this ANOVA table. So ANOVA table is actually can tell us whether the test media or plating method or interaction are significant or not. So based on the p-value, they are all less than 0.05, so they are significant. Now let's have a look at the 2K full 2K factorial experiments. So in this, let's have a look at this problem first. This is a epitaxy layer growth experiment. So this is performed by AT&T. This experiment is based on 2 power 4 design, 4 factors. So we have 4 factors, each at 2 levels. And there will be 6 replicates for each of the 16 level combination data given in the next page. So those are the factors, those are the levels of each factor. Our objective is to reduce variation of y around its target 14.5 micrometer by changing the factor level combinations. Now this is data from epitaxy layer growth experiment. We have the design matrix. So this is our design matrix. 2 power 4 design. So we have 16 runs. So each factor at 2 levels, plus minus, plus minus, plus minus, plus minus. So these are all the possible combinations we have, because this is 2 by 2 by 2 by 2. So we have 16 possible combinations of minus plus signs. So in each level of in each factor level combination, we run the experiment 6 times. We got the thickness for 6 silicon wafers, and this is the average of the thickness. We want the average, the target, close to 14.5 micrometers. So our objective, this is our data. Obviously, we can get a y bar. So let me show you how to get this y bar. So this will be equals to the average between for this row. This is the average. This is the y bar, and if we do this for all the rows, 16 rows, we get all that y bar. If we want to get the variance equals to the variance. So this is the variance. So each level of factor, so this is the factor combinations. So now, in order to get to the main effect of the factor A, what we do is we use this column multiplied by this y bar. So this will equals to this minus sign multiply y bar, and then we will be able to get this column. And we drag it. So this is now we have this column A multiplied by y bar. Now we need to average the we need to average this column. So this will equal to the summation. So we add all everything together because we already have minus sign, plus sign over here. Then we divide by 8. So this will give us the location effect. And however, we can do the location effect. For example, here, if we do the average of this one plus the average of this one, so this is how we do the calculation. We want to see the positive group and the negative group, whether they have significant difference. So this is also the same result. So there are two different ways to calculate the main effect for A. And the same thing for B, we just do the C2. If we double click, so this is the C2 is this cell multiplied by this cell, and we got the B, and then we multiply this whole column with the Y bar, the response, and we got this column, and we do the summation of this column, then divide by 8. Why 8? Because we need to calculate the average for the positive group and average for the minus group. So that's why we divide by 8. In total, we have 16 rounds. 16 rounds, half of them are positive, half of them are negative. So that's why I divided by only by 8, not 16. So how to calculate the interaction effect? So the interaction effect will equals to, for example, if we want to calculate AB interaction. So AB interaction is column A multiplied by column B, and then multiplied by this response. So what do we have? Or we can do something like this. We can insert a model matrix, maybe this one. So we can have AB column. So AB column will equals to this column multiplied by this column. So this will be the AB column, interaction column. And we can also add another column called, let's try four-way interaction. Four-way interaction is ABCD. So ABCD will equals to the multiplication of this guy, multiplied by B, and multiplied by C, multiplied by D. And this will be the ABCD. So in order to calculate the ABCD effect, let's delete it. So ABCD effect will equals to AB column multiplied by my response, and then I do this column. So every entry will be the Y bar, will be Y bar multiplied by AB. So this will be able to give us this AB column. So this, once we get the AB column, what we do is sum this column up, then divide by 8. This will be the location effect. Why we call it location? Because the thickness has a distribution. This is a Y bar is a location, and the variance is a shape. So we are studying the location effect, the main effect of interaction effect AB in terms of the influence on the Y bar, the location. For ABCD, the same thing. What we do is we sum this column up. This ABCD column is actually the multiplication of this ABCD column and the Y bar column. Then we got ABCD column. And this ABCD interaction effect will be sum of this column, because we have minus group, we have positive group, then we add all of them together and divide by 8. So in this way, we got all the location effect, and then you can do the same thing for C, D, AC, AD, AC, or everything every factorial effect. Now, once you got the factorial effect, how do you determine which factorial effect is significant or not? So it's in the lecture notes. So this is all the factorial effects. If they are not significant, so the deduction step, null hypothesis of factorial effects equal to 0. They are not significant under H0. So those factorial effects should be random noise. The normal probability plot should follow a straight line. So the induction step is by fitting a straight line to the middle group of the points around 0 in the normal probability plot. Any effect with corresponding points for all of the line is declared significant. So in the normal probability plot, as we can see, centered at 0, we have a straight line, and any factorial effects D and CD refer off the straight line, so we declare that D and CD are significant. So here, D and CD are significant. Everything else is approximately random noise. So what we want to the null hypothesis is, if all factorial effects are not significant, they should follow this should be just random variations, random noise. But if we have any factorial effects for all of the straight line in the normal probability plot, we will declare those factorial effects are significant. And this is a graphical method to identify the significant factorial effects. Okay, in this video, we finished the two-way ANOVA and 2K experiments.